Okay, well, thank you. Thanks for the kind introduction, and I'm happy to be here. Wait, I have a small problem. It's not the right talk. What happened here? Let me see. Okay, now it's the right talk. Okay, so it's a pleasure to be here and giving you the right talk. So we know that the geometry of space, well, in the old times it was thought to be Euclidean, at least Euclid thought so. But then it was understood that non-Euclidean geometry, there exist also non-Euclidean geometries as possibilities, like hyperbolic space. And artists were like this and drew these nice pictures of hyperbolic space. And then, of course, Euclidean space plus time gave us Minkowski space, or the space-time of special relativity. And this, together with non-Euclidean geometries, gave us the metric of our own space-time, and or the theory of general relativity, or geometrodynamics, the dynamics of geometry. And this theory, of course, had two very surprising predictions. One was black holes, and the other one was the expanding universe. And these predictions were so surprising that Einstein himself was surprised about these predictions and didn't believe them for a while. In fact, I love this phrase that Einstein is said to have said to Lemaitre: "Your math is great, but your physics is dismal." And I like it because sometimes that's told to us, to string theorists. But both involve very drastic stretching of space and on time. So now quantum mechanics and space-time. So of course, general relativity is classical field theory. And we, in principle, since our world is quantum mechanical, we should quantize it. And because it's difficult to change the shape of space-time, I mean, the whole Earth here is barely changing the shape of space-time, then that implies that for most situations, we can approximate physics by saying that we have quantum fields in a fixed background geometry. And we can do that even for gravity or gravity waves. So we can quantize gravity waves just slightly around the background geometry. And even this perturbative simple quantization has very interesting consequences. Of course, this simple quantization is not enough for some problems. So for example, for the beginning of the Big Bang, we would need a full theory of quantum gravity. But even this perturbative approach has some interesting consequences. And I'm first going to talk about those consequences. And so I'm going to just discuss a couple of, remind you of some predictions from the perturbative quantization. And yeah, so I'm not controlling the lights.
Somebody is standing there without realizing that you are changing.
But that's fine. It gives this.
Against the wall, you are switching the flipping the switch.
Yeah. So. Okay. So the two surprising predictions are that black holes have a temperature. So they're related to the classical predictions, surprising predictions, and the other one is that the accelerating universe also has a temperature. So the formula for the temperature of black holes was derived by Hawking, and it says that the temperature is related to the size of the black hole. So the smaller the black hole, the higher the temperature. Or in other words, the wavelength of the radiation emitted by the black hole is proportional to the size of the black hole. And another prediction was that an accelerating universe also has a temperature. And it's given by the same formula. And I wanted to show the similarity between these two formulas just to emphasize that these two effects have a very common origin. And you should view them as variations of the same effect. And it's very difficult to measure. I mean, it has not been measured. This effect of that black holes have a temperature has not been measured for astrophysical black holes. But this fact that an accelerating universe has a temperature is actually very relevant for us. And that relevance comes from the theory of inflation, which is the leading theory to explain one feature of the universe that I'm going to mention in a second. So the period of inflation consists in a period of expansion previous to the Big Bang phase with constant acceleration. And if we have the theory of inflation according to classical physics, it would produce a perfectly uniform universe and an homogeneous universe. And this more or less agrees with roughly the universe at long scales is fairly homogeneous, but it's not exactly homogeneous. And in order to get it not to be exactly homogeneous, you need these quantum fluctuations or temperature fluctuations. And so, in fact, quantum mechanics is crucial for understanding the universe at very long distances. And so we think that this long-distance structure, or this type of maps that CMB experimentalists have been measuring, are a reflection of the quantum fluctuations at the beginning of the universe, and that the structure of the geometry of spacetime at long distances, this picture reflects the structure of the geometry of the spatial slices of constant density in the universe. And that, for that structure, quantum mechanics is very important. And I think this is quite surprising. So usually we're thinking that quantum mechanical effects for gravity are very relevant at very short distances. So you probably heard this before. And I wanted to emphasize also that they are important for long distances. And they are not only important, but they are crucial for understanding the universe as we see it today. Now, okay, so that was one point about the connection between quantum mechanics and the geometry of the universe. And this is, an experimental fact. We have this geometry of the universe, and we think we explain it using quantum mechanics. So this is not, well, it's a speculation that inflation is correct. So the origin of these fluctuations might not be inflation, but it's the simplest theory that we have today for explaining them. Now, I'm going to move slightly into a more theoretical direction. So we are going to discuss one feature of these fluctuations, just as a lead-in for something I'm going to discuss later. So these fluctuations are nearly scale invariant. So that means that the fluctuations at very different distance scales are similar. So if you have a fluctuation with a very long distance, fluctuation in the geometry, the probability of having a fluctuation, or the amplitude of having the fluctuation with a shorter wavelength is basically the same. So psi here, imagining the probability amplitude for the shape of the universe, for each possible shape that this map can have, each possible distribution of black and red dots. So, red and blue regions, which represents positive and negative amplitudes. And that scale invariance in physics is common in many other systems. So scale invariance, so just to define it more precisely, is the statement that if we rescale all coordinates, we have the same physics. And an example of a scale invariant system that you're familiar with is the electric force. And most of everyday physics is not quite scale invariant. And so we have very poor intuition, especially for interacting scale invariant theories. So, atoms come with specific sizes and so on. So most of our everyday physics is not scale invariant. But there are some systems, some special systems, for example, condensed matter physics at second order phase transitions, which are both interacting and scale invariant. There is, for example, the theory of chromodynamics, the theory that describes strong interactions at high energies, becomes almost scale invariant. So those are examples of theories that are scale invariant. Now, sometimes people also talk about conformal invariance. This is just simply other transformations. You can do other changes of coordinates that preserve the angles. And here, Escher wrote this picture where he applies such a transformation to an ordinary scene. But that's what the word means. Conformal invariance will not be crucial for what I'm saying. I'm just saying for completeness. Because I'm saying it because many theories that are scale invariant are also conformal invariant. But that's a small detail. Now, we saw that the wave function of the universe was a scale invariant function of geometry. But we can also generate other scale invariant functions of geometry by thinking about the scale invariant field theory on a general geometry. So we could imagine doing the partition function or statistical mechanics of some field theory, let's say the statistical mechanics of the icing model or of the water vapor phase transition.
Well, I have a question.
Yeah, please.
The statistical invariance of the universe The
Yes.
scaling for the universe,
Yes.
is that an experimental fact? Is that a hypothesis? Or is that a theoretically derived
Uh,
result? You
yeah,
started
yeah.
from
I
there,
started
how
from
much
there.
information is-
No, it is an experimental fact.
You mean somebody has gone through WMAP in great details and
Yes,
found
yes,
some invariance?
yes, yes. It's nearly scale invariance. So it's
Even before that, so
Yeah, no, I
Yes,
know it was
yes,
known, but
yes.
now people accept it as a...
yes, yes. It's nearly scale invariant. So there is an exponent, and so let's say scale invariant will give you 0,
Yeah.
and it's the deviation of 4% away from 0.
Because in condensed matter physics,
Yeah.
getting an exponent for helium,
Yes.
this guy spent all his life, I forget his name, he was in Santa Barbara.
Yes, yes.
To get exponent up to where all these corrections, it takes a very long.
Yeah. So in the context of yeah.
Establish it. It's not a trivial
Well,
statement.
well, okay. So let me say what the statement is in a little more detail. So you might have seen these plots of the power spectrum of the CMB that you have some peaks like this. I'm sure you've seen these pictures, where this is the amplitude of the fluctuations, and this is the angular the angular scale on the sky. Now these peaks come from the particular physics of recombination. So you start with some picture which roughly is constant here, and then because at the time of recombination you have special horizon size and so on, it produces all these peaks. But the underlying fluctuations are scale invariant, nearly scale invariant. There is a small slope.
And people have processed the data looking at higher moments and so on. They know there is no intermittency and so on and so forth.
Well, this is the 2-point function of the scale distribution, and then you can look at the 3-point function. And so people have looked at the 3-point function. The 3-point function is 0 to the accuracy that where here 0 means that the deviation from a Gaussian distribution is roughly 10 to the minus 4.
Okay, that's what I'm asking.
Yeah.
So people have looked
So,
at even deviation
yes.
from Gaussian.
Yes,
Not a
yes,
straight
yes,
exponential.
yes.
There is
Yes,
no
but this
intermittency.
initial distribution is Gaussian to the accuracy that's been measured, and it's measured with very high accuracy. So it's 10 to the minus 4 deviation from Gaussian.
Okay.
Yeah.
So the data are good enough to do that, because you need very lot of data to do that. But data
Yes,
is
yes,
not
yes.
good
They
enough.
have lots of data, so they are measuring angle. I mean, yeah. You have about more than 1 million pixels on the sky. Yeah. Okay. Good. I mean, in fact, this fact that it's nearly scale invariant is and it's almost Gaussian is also in agreement with the theory of inflation. So that's why when people say that this is a good candidate theory, it's for these reasons. If you were to improve about 2 or more orders of magnitude, you would be able to start seeing some deviations from Gaussianity, which are also predicted by the theory. Anyway, so yeah, there are lots of signals you could. Well, anyway, we could go. But so you could also get the scale invariant theory of function of geometry by doing statistical physics, and this is another way of getting. And so you might wonder whether the wave function of the universe could also be obtained in this way, and this would be like the more fundamental description of the wave function of the universe. Now we don't know whether this is true or not, and probably I should have left this for the speculation part of the talk, but I wanted to put it as a motivation. And some people say maybe it's true, some people say maybe it's not true, but well, this is something we ignore at the present moment. And there was some very weird theory of gravity that perhaps you can think of this way. But the interesting thing is that though it doesn't work for de Sitter space, it does work for anti-de Sitter space or for hyperbolic space. So the space of an expanding universe that we discussed, the space of inflationary physics during the time of inflation, is pretty close to this space. So this is a space that expands forever, where you would get things that are exactly scale invariant. As I said, inflation is not exactly scale invariant, but it's close to this space. So it's a space where you have the directions of space, and they are expanding exponentially as time progresses. Okay. There is a closely related space, which is Euclidean, so it has Euclidean signature. And it's the same thing, but with a change in this sign. So you have some directions of space, and as you move in an extra dimension, those directions are also expanding. And then there is another space, which is called anti-de Sitter space, which is very similar to this one, except that one of the coordinates here you turn into time. So this is a space where you have spatial sections which look like Minkowski space, and then as you move along the radial direction, they're also expanding. So all these spaces are not equal to each other, but they are closely related. They all have constant curvature, and they have lots of symmetries. Just wanted to point out the similarity that they have between them. And the idea is that in the case of anti-de Sitter space, one can view the wave function of the universe in these spaces in terms of the wave function of a theory on the boundary of these spaces. So you can have a system on the boundary, and that system on the boundary describes the gravitational physics in the interior. This is also called the gauge-gravity duality, or gauge-string duality, or ADS-CFT, or holography. It has many names. And it basically says that quantum field theory or quantum theory doesn't have to be a field theory. It could be a theory of a quantum mechanical system. So all these are theories of quantum interacting particles, interacting systems, quantum systems, are supposed to be equal to theories with dynamical space-time. And in some particular cases, it's a theory close to general relativity. In some other cases, it's some kind of string theory. And in the most general case, we don't know exactly what it would be. But we think that probably any quantum system would have some kind of gravity description, though the gravity description could be very weird. But we have some very concrete examples of quantum mechanical theories that have very concrete gravity or string duels. And when this quantum mechanical system is very strongly coupled, so the degrees of freedom are very strongly interacting, then, well, of course, this continues to be a concrete model that might be hard to solve, might be hard to analyze, but is concretely defined. And that's supposed to be equal to a theory now of Einstein gravity. So here, when the coupling becomes very, very large, then the string effects are not important. And if you've never heard about string theory or don't care about string theory, then you can forget about it and deal just purely with the theory of Einstein gravity plus some other fields. So it could be Einstein gravity plus a scalar field, or you might also have an electric field, and so on, depending on the circumstances. So, for example, so you could have a bunch of harmonic oscillators and Majorana fermions. So we have a bunch of harmonic oscillators and some fermionic harmonic oscillators, or sometimes called system of spins, essentially. And then one can add some interactions. So we can have some anharmonic terms. So we have an x to the fourth term in the interactions. And also similar some interactions between the harmonic oscillator variables and these fermionic harmonic oscillators. And if you choose these interactions correctly, then this system you can always define for any interaction. But for a very special class of interactions, you will have a gravity dual that I mentioned in a second. And so what are those special interactions? So those are special interactions that preserve certain symmetries. So you have to start with not just one harmonic oscillator, but many of them. So there's an index that goes from 1 to 9, and some index here, A, which is in the adjoint of UN. So there are n squared components of these harmonic oscillators. So we have 9 times n squared components of harmonic oscillators. That's the total number of oscillators, harmonic oscillators we have, is times n squared that we started before we introduced interactions. And then we introduced interactions, and we have some interacting system. Now, all these interactions are just determined by this UN symmetry, so that rotates all these n squared components, and some symmetry called supersymmetry. So if you never heard about supersymmetry, it's some simple symmetry that relates bosons and fermions and determines all the interaction terms. Okay? So here, the role of supersymmetry is only to determine completely what the interactions on this Lagrangian is. So it's some Lagrangian. Okay, so it's a little exotic in the sense that the interactions are constrained by some symmetries we've never heard of, but it's conceptually not very complicated, right? It's simply a bunch of harmonic oscillators with some anharmonic interactions. Okay? And the geometry dual to this is some kind of black hole. So especially when you consider it at finite temperature, so you can consider that previous system at finite temperature. And then the geometry is some kind of black hole. It's 10-dimensional, but basically there are two important directions, which are the time direction and the radial direction of the black hole. And then there is an 8-dimensional sphere. And the previous system had an SO9 symmetry, and that's the rotational symmetry of this sphere. And this, the curvature radius here in this region is related to the effective interaction strength of the system. So this interaction strength, in this case, in the system depends on the energy scale at which we probe it. So if we are asking what is the interaction strength at the temperature scale, then it could be very large. And in that case, here the curvature at the horizon will be very small. So when the interactions are very large, this is a black hole which we can describe using an Einstein theory of gravity in 10 dimensions with specific matter content. This particular theory is related to string theories, to the 10-dimensional string theories, but it's just an ordinary theory of gravity. And we can calculate, just to show you how you could test these relationships, you can calculate the entropy and the free energy of this using the Hawking-Bekenstein formula for the entropy of the black hole. So there is basically it's related to the formula that Hawking derived for the temperature. So you can calculate the temperature for this geometry as a function of the mass. And from this, you can derive all the thermodynamics relationships for this system. You can calculating the temperature as a function of the mass is equivalent to calculating the entropy as a function of the temperature or the mass. And you can compare this to a direct computation in the quantum mechanical model. So you can take that quantum mechanical model and do the computation numerically. And this is what you find. So you find here are the numerical computations are here. And this is the gravity prediction. Right? Now, it doesn't seem to agree exactly. So you might be slightly worried in the beginning. But you should remember that this was supposed to be true at strong coupling. So strong coupling in this context means very low temperatures. And indeed, as we lower the temperature, they tend to agree a little more. And the relationship also involves a little bit some string theory. So if you include the leading stringy corrections, you find that you have this dotted curve which agrees a little better. So you see that how you see both the agreement at low temperatures and some kind of disagreement at higher temperatures where it's not quite Einstein gravity. So you see that as you increase the interactions, you have better agreement and so on. This is some example. I mean, there is a lot of evidence for in other examples, but I chose to show you one particular case. Okay, so now I'm going to discuss some other topics. So we discussed a bit about holography and the relationship between.
Could I ask a question?
Yes.
Last thing?
Yes,
so
please.
that seemed to be a very specific model. Of course, I'm sure
Yes.
I'm missing a lot.
Yes.
I mean, it's a very specific
Yes.
model with Majorana fermions
Yes.
and particular
Yes.
coupling
Yes.
and harmonic. I mean, and this is beautiful, but
Yeah.
what does it prove? I mean, it's just a specific model.
Well, so it's a very specific model that has a gravity description. So it shows that there is a specific model that has a concrete gravity description.
Right.
It's not that we have, there is some model and there is some gravity and there is some relationship.
It's not fine-tuned. You choose a model. And
you choose a model and that particular model has a gravity description that we know.
The same model you're solving two
Now,
ways. That's the point.
Yeah, that's the point, that there is a relationship with very concrete example. There are other concrete examples. I chose these particular
there are other
ones.
examples also.
Well, there are other examples based on field theory, and I didn't choose those because I thought people might be more unfamiliar with. If I chose, let's say, well, the other example the most studied example is one that involves supersymmetric QCD, but I thought that harmonic oscillators would be more closely connected to what people know.
Following up that, right?
Yes.
I could see the large N
Yes.
approximation.
Yes.
giving,
Yes.
Semi-classical gravity.
Yes. Yes.
Proven earlier. And then fermion plays the role of what in this case?
Well, in all the examples that give rise to nice Einstein gravity duels, you have bosons and fermions and some degree of supersymmetry. That's from the examples we know. There might be more examples we don't know. And so maybe some of you can come up with an example that we don't know. So we have one mechanism for generating examples, which is to take some configuration in string theory and take some near horizon limits and so on. Some objects that we can view as black holes. And so there's some techniques, and those techniques, because they are based on this 10-dimensional string theory, they have some degree of supersymmetry. We can break it slightly and so on, but they will have these bosons and fermions. And these are all the examples
So all the
we
examples
know.
have supersymmetry as a given.
All the examples that give rise to Einstein gravity. Yes. There are other examples that are kind of similar to gravity. So there's a nice example that was proposed by Sachdeva and Ye and Kitaev that has only fermions. but doesn't reproduce all the features of gravity, but some features. So yeah, that's where we are. But
it's the most economic toy model that you can use.
well, this is a toy model I can describe. Well, I don't have to talk about quantum field theory, it's just quantum mechanics, so that's why I chose this one. But it's not the most studied. So the most studied is the four-dimensional supersymmetric QCD example. It has a little more symmetries than this one, so that's why it's been studied more. Okay, so here we discussed in detail this, well, in some detail, this relationship between quantum field theory and gravity, and we saw that black holes have also some relationship to quantum systems. And in fact, there is a whole series of relationships. There are also some kind of similarities to non-trivial phases of condensed matter physics, and there are some connections to quantum information theory, entanglement entropy, computational complexity, quantum error correction, and quantum chaos. And they're all related to each other in some way. And I will not describe all the relationships. What I would like to do is I like to show some case examples, so some concrete examples where you'll see how these relationships work. And the important thing here is that by knowing that things are related, sometimes you can learn some things about one of these topics. Let's say I'm going to discuss a little bit about quantum chaos. That by exploring these relationships, you will learn something about quantum chaos that is true in general, is independent of the relationships in principle, but whose discovery was related to exploring these relationships. So knowing and exploring these relationships was useful for deriving some interesting property about quantum chaos. So that's what will be one of the examples I'll discuss, and then I'll discuss some other examples later. Okay, first example. So the first example is a certain universal bound on quantum chaos that was inspired by black holes. Okay, so let's start with classical chaos. So the initial development of classical chaos is related to the divergence of nearby trajectories. So you have two trajectories, so you have one trajectory in phase space, and you make a small deformation, and then so you take some trajectory, you kick one of them, and then after a while, the position will be different. And then you can define typically, this deviation will grow exponentially in time, and you can define a Lyapunov exponent. And so you can think of this as, well, mathematically, you can write this as, so the variation that you have here at time t, due to a perturbation at time 0, you can think of it as the Poisson bracket of the variable at time t and the variable at time 0. This could have any sign, so you could take the square, for example. That will be positive. And in the quantum case, you can similarly write, instead of commutators, instead of Poisson brackets, you can write commutators. And so you can consider the commutator between two variables, or if you have many particle system, between two different operators corresponding to two different particles. So you perturb one particle, and then there is some effect on the other. And you take the square of these commutators, and those will be positive operators, and you can take the expectation value either in some state or in a thermal state. And so if you take it on the thermal state, you are taking the average of this commutator, and you are seeing how it grows in time. So in the time equal to 0, you could, these two operators, for example, commute with each other. But as time progresses, there will be a growth in the commutator. The commutator will be small, so typically suppressed by the number of particles or the entropy of the system. But it will grow exponentially. So in general, we think of this as two simple operators, so initially commuting observables. And we imagine we have some large entropy system. These commutators typically will start growing exponentially, and we define the coefficient of that exponential growth to be the quantum version of the Lyapunov exponent. Now it's defined by its initial increase. I mean, it will not exponentially increase forever, like most exponentials at some point will not. And at very long times, this will saturate to a quantity of order 1. So somehow that will be, if these are operators which are like Pauli matrices, for example, their commutators cannot be bigger than 1, so it will saturate to some quantity of order 1. So a commutator will be something where starts 0, and then it grows exponentially, but with a very small coefficient, prefactor. And eventually, after some time, proportional to the logarithm of the entropy, it will stabilize and will become of order 1. So now, that's the definition of this observable, so it can be done for any system. And now we will use this gauge cavity duality or ADS-CFT and black holes. So we have black holes in anti-de Sitter space, or in these gravity systems dual to the field theory on the boundary, can be viewed as thermal systems, some fluid or some system made of very strongly interacting particles. And so we're imagining we're doing exactly the same computation we did before about the commutator, but we're going to use black holes to do them. So we're going to imagine that the system we have is dual to one of these black holes. So, and the two operators will correspond to some simple operations that insert, let's say, one particle. So it's a small change in the system, and the small change will just introduce one particle in the bulk. So it will create one small perturbation that moves here in the bulk. So the action, for example, of this V of 0 will produce one particle that moves in the bulk, falls into a black hole horizon. So here the vertical direction is time, the horizontal direction is space, and this 45-degree line represents the horizon of the black hole. And then W of t will similarly create a particle or absorb a particle that might have been produced earlier. So acting with W of t on a state will produce a particle, and if we volve that backwards, it will give a particle that travels backwards here and intersects the previous particle. Okay, and in order to compute the commutator, computing the commutator ends up involving in calculating the scattering amplitude between these two excitations. So the influence that one has on the other, it's reasonable that it will involve the scattering amplitude. Now here, letting a large time pass by here means that these two particles, so one important property of black holes is that the time as measured far away here is represented in the near horizon region as the boost angle. So as so here time translations leave this point invariant and act as boosts on this near horizon geometry. So near horizon geometry is just flat space, but these time translations are acting as boosts on this near horizon geometry. And therefore, when these two particles have a large relative time separation here, it means that they are colliding here with very large relative energies because they are very boosted relative to each other. Okay, so then the leading interaction, the interaction that will be the one that grows fastest with energy. And that is the graviton exchange. So if they exchange a scalar or a photon or whatever, that grows less with energy. And gravity is the interaction that grows fastest with energy. And that comes from the fact that the graviton has spin 2. And this interaction is something well known in GR. It's just the so-called Shapiro time delays when you have some, let's say even for the sun, if you have some particle that moves past the sun, it suffers a small time delay. And that time delay is proportional to the energy. And here, the center of mass energy, and that center of mass energy here grows exponentially with time because of this boost property that we discussed before. And so we expect that the commutator will grow in this way with a coefficient that is simply given by the Hawking temperature. So here, I wrote it in terms of units where the temperature is 1, but when you restore the factors of the temperature of the black hole, you find that the Lyapunov exponent is given in terms of the Hawking temperature of the black hole. So this relates this chaos-like property to a thermodynamic property of the system, the temperature. Okay. So and it gives us a very specific exponent. It's not that we can vary this exponent. It's just one value. Now the question is whether it can be different. So I mean, in ordinary systems, this exponent can be different from this value. If we have a very weakly coupled system, this exponent can be very small. Now, in this case, we said that the graviton leads to some scattering phase or scattering phase shift, which is proportional to the center of mass energy. But if instead of having gravity, we, let's say, have strings, then you have slightly different answer. And the slightly different answer is a different power of S. I don't expect you to follow the details. Just believe me that it's different in string theory. But the important point is not so much that it's different, but well, first of all, it's important that it's different, but it's also smaller than the value in gravity. Okay? Okay, so we can get something different, and we see that it can be less than this value, and we can ask whether it could be more. Now, if we were in flat space and we scatter two particles, and this phase shift were to grow with a power of s which is bigger than 1, than the one in gravity, then it will lead to some kind of causality violation in the theory. So it will lead. For that reason, we expect that the exponent should probably be less. Okay, so maybe there is a bound on this exponent. So that's what we get by analyzing this in gravity and using these gravity-like arguments. But then you can go back to quantum mechanics and then prove just using properties of the quantum mechanical system in Euclidean time, like analyticity in Euclidean time and unitarity, and some physical assumptions that simple observables thermalize, in order to prove that actually this exponent, this bound, should always be less than the temperature. Okay? And this here doesn't use gravity. This is just something you prove using standard quantum mechanical tools.
So should one worry about the fact that at least for interacting quantum systems, we do not really completely understand thermalization at this stage, right?
Right.
Localization. Should I worry
yes,
about
yes.
it in this context?
Well, we are assuming that that there is simple observables thermalize with an exponent, with some exponent which is finite in n, so it doesn't grow with n. Okay, so that's an assumption. So if the system does not obey this assumption, then it might be violated. Yeah, so that's the situation. But I want to highlight here how these relationships were used, right? So we have some observable, we translated it to gravity. We could compute it relatively easily in gravity, and then in gravity it had certain properties. And then from there, one could go back and try to prove those properties in general, perhaps. You can make some hypothesis. And so this is a way in which these relationships can be useful for learning about systems that have nothing to do with gravity.
Does this just hold in the semi-classical limit, or does this hold in the general limit?
No, this holds more generally, but in particular, it also holds for semi-classical limits, like in a quantum billiard. So if you have a quantum particle moving in an irregular box, then it also holds. Though that system has nothing to do, no simple gravity description. But it's actually more, we expect it more to be saturated in very quantum mechanical, strongly interacting systems. It always involves large n, so some kind of large n or small h bar limit in order to have the separation of scales between the time that it takes for the commutator to start growing to the time it takes to saturate.
That's kind of what I meant by semi-classical.
Good. Yes, you need that. You definitely need that. So you need that the commutator will not saturate immediately, but it will take some long time to saturate. Otherwise, you cannot define the Lyapunov exponent. So the concept itself is not defined. Okay. So you should think of these as systems that have many parts, and you just change one little part, and the inference of this little part takes some time to spread throughout the system.
And is it a leading order result following up on that? I
Yes.
should think of it as leading order h bar result, just 1 over n?
Yes, it's a statement about the 1 over n result.
Right. So
Yeah.
do you know anything about the next to leading order correction and so on? Is anything known that the system is well behaved? It's a technical question. But
Yes. No, I don't know. Yeah, so here we are assuming, maybe I should go to the previous, let me see. Well, anyway, I lost the place where. Here it was, yeah. So it's important there is a 1 over s here. So, and that 1 over s gives this long time separation. So you can follow this exponential for many e-foldings of the exponential, right? To define the exponent before it saturates. If s was of order 1, then this would be very small, and there will be just one e-fold, and that's it. And you can define the exponent very well. Okay, so now I'd like to move on to another topic, which is the relationship between entanglement and geometry. Now, the entanglement pattern present in the state of the boundary theory can translate into geometrical features of the interior. And this leads to the idea that spacetime, or the emergence of spacetime, is connected to the entanglement properties of the fundamental degrees of freedom. So we have some theory like this system of harmonic oscillators, and then we have the higher dimensional space. So what is how is the higher dimensional space related to the quantum mechanical degrees of freedom of the boundary theory? Now the short answer is we don't know. But I'm going to try to show you what things we do know. So some aspects that we think we know about this relationship. So first is a very interesting formula that was derived by Ryu and Takayanagi, was proposed by Ryu and Takayanagi, which is about the entropy of subregions. So this is especially simple in cases where you have, let's say, a one-dimensional field theory. So you have, let's say, a spin chain or some one-dimensional system. So this is one-dimensional space. So the blue thing is the boundary, and then there is an extra dimension, which is the gravitational theory in the interior. Then if you focus on, so you could consider the ground state of the whole system, but if you focus on a small region of the state, and you restrict the state to this small region, that state might be mixed and might have some entropy, and in general will have some entropy. And in cases that have a gravity dual, you can calculate the entropy of this subregion by looking at the minimal surface in the interior with minimal area that ends on the boundary. And you apply a formula which is similar to the Hawking-Bekenstein formula for the black hole entropy, which says that the area, you take the area of that minimal surface, divide by g Newton, and that gives you the entropy of this system. Okay? So this is a generalization of the formula of the Hawking-Bekenstein formula. So the interesting aspect of this formula is that it relates entanglement properties of the state in the boundary to geometrical features of the theory in the interior, because in order the area of the minimal surface and the shape of this minimal surface will depend on the geometry in the interior. And this has been used to study various things and with various applications and so on, which I will not dwell on. I'm going now to go to a very extreme case of this, which is the relationship between wormholes and entanglement. So we can consider the simplest black hole solution, the empty black hole solution in, let's say, anti-de Sitter space or these spaces with a boundary. And those black holes really, those solutions really contain two black holes. So the maximally extend, even the Schwarzschild black hole solution, if you maximally extend it through the horizon and you don't put any matter in the interior, is a solution which contains two sides. So it's really two black holes, a right exterior and a left exterior that looks similar to the right, looks essentially identical to the right exterior, and they are joined through a wormhole. Okay? So this surface here, this blue surface, is sometimes called the Einstein-Rosen bridge. It joins the two asymptotic regions of space. That's some surface of space at one time, and then this surface, of course, could evolve, and so on. And the idea is that this geometry, which is connected between the two sides, should be viewed in the quantum mechanical theory as an entangled state of two completely non-interacting systems. So the idea is that there is some left system of, let's say, harmonic oscillators or whatever that it has some Hamiltonian on its own, and then some other system that has a separate Hamiltonian and with no interaction between them. But we consider them, we start them in a particular entangled state, which is this entangled state. This entangled state, sometimes, well, it's called the thermal field double. It is useful to introduce it to deal with thermal field theories, to introduce a fictitious copy of the theory. But in this case, we could think of the two copies as physical, and then we have this particular entangled state, and we have this description for it. I guess we call this ER equal to EPR, because Einstein, Rosen, and Podolsky also wrote a paper in the same year talking about where they introduced the famous entanglement notion. So in other words, we could have two systems far away from each other. One has a gravity dual that is some particular geometry. The other one has a gravity dual which is some similar geometry to two identical systems. And if they are entangled, then these geometries will be connected through the interior. Okay. Now, just to highlight what this is, let me. So imagine we have. Well, I'm not sure whether I should tell you this. Well, Now, one important property of these black holes is that you cannot send signals from one side to the other. So if you try to send the signal from here, from the left to the right, you cannot do it. So you send the signal from here, it comes in here, and the black hole collapses, the wormhole collapses before you can come out, right? So then you could ask, well, in what sense are these two connected? So the little story that I'm going to tell now is just to explain in what sense they are connected. So this is a science fiction story where we have Romeo and Juliet, and their families wanted to keep them apart, so they send them one here, the other to the Andromeda galaxy. But these two people are very smart, and they managed to share a bunch of entangled qubits as messages, and they managed to build two big black holes that are perfectly entangled in this system. They have very powerful quantum computers to do this. And after they do that, so they will have the two black holes, one here and one in the Andromeda galaxy. And they each position themselves, let's say, outside the black hole. So they're very far away in the ambient space, but through the wormhole, they're very close to each other, right? And then they decide to jump into the wormhole, and they meet in the interior, okay? So their families see that they jump into the wormhole and they died, right? So, and the person telling the story would also write the same thing. Okay, that was a literary reference. But they met in the interior, okay? So they really met in the interior. Okay, so that shows you in what sense there is a shared space-time here in the interior. They could really meet in the interior in principle. Now, I mentioned this fact before, that you couldn't send the signal from the left to the right, but you could almost barely send the signal, right? So it is pretty close. I mean, if you send it very early on, almost if you were to move a little bit beyond this light cone, you could send the signal. Now you might worry, well, perhaps if I send some matter in and there is some scattering and so on, perhaps I can move this outside. And you could change the solution a little bit in such a way that you could send a signal. But actually, there is a so-called null energy condition, which says that the integral of along a null line of the stress tensor component, that's a long line we define to be x minus, the t minus minus component of the stress tensor, integrated along that line, should always be positive. And this is now a theorem that was recently proven for arbitrary field theories. So for a while in the past, people speculated, oh, maybe quantum corrections could lead to stress tensor which is negative, and if it was negative, then you could make the wormhole traversable. But in any field theory, this conventional field theory, this is positive, and then they are not traversable. Okay, so that sounds not good for science fiction, so we can have a traversable wormhole. But they are interesting for science. But actually, there is some way of making the wormholes traversables, and this is related to quantum teleportation. So first, let me remind you of quantum teleportation. So this was introduced by these people here. Unfortunately, you can't read their names. Bennett et al. In the 80s, I think. And so the idea is the following. So we have some person here, let's call him Bob, and Charlie gives him a qubit, okay? And Bob wants to send the qubit to Alice, okay? And he can do it in the following way. So imagine that first Bob and Alice shared an entangled qubit. So they arranged and they share some other pair, entangled qubit. So this is another pair of qubits separate from this one, and in some known entangled state. Then Bob can take Charlie's qubit and make a joint measurement of these two qubits and produce 4 possible answers. So measurement that has 4 possible outcomes. And then he sends the 2 qubits of information to Alice, and Alice does some operation that depends on this these 2 qubits, these 2 bits, sorry, classical bits, and then Alice recovers the Charlie's qubit. Okay. So the interesting thing about quantum teleportation is that you can send the qubit by sending just 2 classical bits. Okay. Now, naively, you might think that if you want to specify a qubit, you need to specify an infinite amount of variables, right? Because you need to say where it's pointing and so on. But if you are sharing this entangled, so here the magic is that this is done by sharing this apparently unrelated entangled pair. Okay, so that's quantum teleportation, and hopefully you've heard about it before, because I didn't give you the mathematical treatment to convince you that it is true. But it's a surprising quantum mechanical effect. And you can understand it simply by, well, you can read in their paper or understand it simply in terms of the qubits. If you want, you can ask me to do it. Okay, but it's a little funny how this qubit travels, right? So it seems to, I mean, sometimes people would draw a picture, a continuous line where this qubit somehow travels here backwards in time and goes back to Alice. And also, let's say someone tells you that that they want to teleport you, right? Now, here, the teleporting consists in some measurement that completely seems to destroy the two qubits, right? And give some classical answer. So you might be a little worried about being teleported, okay? Through this method. Okay, they guarantee you they will reassemble you here, but it might seem that it might be painful, at least at this moment. Right? Okay, so that's some background. Now let's analyze this in this context of the wormhole that we discussed. So we have, now Bob has a system that has a gravity dual, and Alice does the same. And they put it in this thermofield double. So this is, again, the system whose gravity description is this wormhole. And then we have Charlie's qubit. And so this Bob can send the qubit here at early times. And what he can do is he can measure here something on the left exterior, so the value of some field, for example. And he can send the classical result of this measurement back here to Alice. And Alice can do some operation. And this operation has the feature of introducing a negative null energy wave or shock wave here. And this negative energy pulse can now send the qubit that was here behind the horizon to outside the horizon. Okay. And this negative energy pulse, I told you there was a theorem before, but the theorem is violated here because there is some connection between here, a causal connection between the left and the right side. Okay. So it's a causal from the point of view of causality here in this geometry, but from the point of view of the lab, right, the speed of light that we have here in the interior is completely unrelated to any possible speed of light here on the boundary. So this could be two non-relativistic systems, as these two systems of harmonic oscillators as a system of harmonic oscillators we described, and has no connection to the speed of light in the interior. So this person can really do the measurement and send it to the other one. There is no problem with this setup. So this teleportation through the wormhole was something that Gao, Jeffreys, and Wall in a very nice, interesting paper discussed. So here we have all the elements of the teleportation that we discussed before. So we have the entangled state, was the thermofield double that we initially had. We have a simple operation, which is sending in the particle. Then here, the time evolution here pushes this particle here into the interior. And in the quantum mechanical system is scrambling. It's mixing this object that you sent with all the other degrees of freedom. And so then it is such that when you do a simple measurement here, it's really a joint measurement of the spin you sent and many other measurements, and the other spins that were forming part of this quantum state. Okay. Then you send the classical information. And then here, just the natural time evolution aided by the operation that Alice did here really is the thing that unscrambles and pulls out this qubit from the rest of the qubits. And here, from the point of view of the geometry, there is something very simple that happens, is that this qubit here simply sails here and encounters this shock wave, which pushes it outwards. Now, the shock wave might be a little painful to you, so if you were teleported through this wormhole, the shock wave might be slightly painful. But if you were in a two-dimensional black hole or in a higher-dimensional black hole, but the perturbation that Alice and the measurement that Bob does and the perturbation that Alice does is an S wave, so it's uniform in space, then you don't actually feel this shock wave. So it's just some coordinate change. You just go through it and feel perfectly happy. In fact, you don't feel anything at all, in this case, when you are teleported. Okay? So it feels as if you are traveling through empty space. While from the point of view of the boundary theory, something bad is happening to you, right? You are being thermalized and so on. So it's, this is general relativity, right? So that your description is very different from the point of view of the bulk observer and the point of view of the boundary observer. And I think we still would like to have a better description of how to join this gravity description with the ordinary boundary description of this teleportation process. I mean, it's really all about the feelings in this case. It's the feelings of the observer as he's being teleported. So what's interesting here is not that, I mean, teleportation we knew for a long time, so that's not what's interesting. What's interesting is how it's been teleported. It's been teleported by going through a wormhole, okay? So this shows, in some sense, that these wormholes have some reality to them, in the sense that, well, some object can go through from one side to the other, and that's what happens with teleportation.
So on this point,
yes.
What the boundary people in calculating
Yes.
thermalization is
Yes.
not a true representation of what the real person went through.
No, it is, well, in principle, it's supposed to be completely equivalent, and it's supposed to be also true representation. And the thermalization is what the person from one side sees, right? He saw that thermalization.
They are only on one side.
Yeah, that's right. So that's the description from one side. When you have the two sides, you have this wormhole. And I think it would be nice to have a quantum mechanic to maybe either extend quantum mechanics. Well, this is speculation. Either extend quantum mechanics or view this quantum mechanical process in some way where it's more manifest that what's happening is what we see in the bulk.
Way, right? Like Bill Andrew trying to get the left and right combination and
Yes.
make a different representation. Maybe you get a result that's closer to the truth.
Well, we have one description, which is the bulk gravity description. And we have, let's say, a conjecture that the two are related, and we can do some calculations in many systems and check that we get similar answers. But we don't have an easy way to understand all the features. Okay. Now, I wanted, since I'm told that clock is advanced by half an hour, I think. No, I'm just kidding. Yeah, I'm about to end. I wanted to just mention one thing about one of the ideas. So I finished this discussion of wormholes. I'm going to just mention one thing about tensor networks and geometry. So tensor networks are some efficient representation of the wave function of complex systems in terms of simple parts, and they were introduced by people who were doing numerical simulations of wave functions of systems. And the idea is that we can think of these networks as giving some kind of discretization of the geometry. So it looks, in many cases, so you can think of the bulk spacetime as made out of discrete units, and each discrete unit is a tensor that builds up the wave function. Unfortunately, I'm giving you a very rough idea, so if you haven't heard it before, you might find it hard to understand. But I wanted to highlight, and Brian here might probably or perhaps already has given you a better description, a longer description of this. He was the one who noticed the similarity between these tensor networks and the geometry of the geometry in ADS-CFT. And this picture realizes many of the properties of ADS-CFT, not all of them, but it realizes many, and it's conceptually very nice, and probably in the future will develop in a very nice way. So in conclusions, we highlighted a bunch of points, somewhat slightly disconnected, but they're all related to quantum mechanics and the geometry of spacetime. The first was the fact that we use quantum mechanics to understand the large-scale structure of our own universe, so this is not a speculation. We also theoretically know that certain strongly interacting quantum systems have concrete gravity duels. We also highlighted the fact that the near horizon dynamics of black holes is related to the chaotic dynamics of quantum systems and this Lyapunov exponent. And we highlighted the fact that the structure of spacetime is intimately related to entanglement patterns in the quantum state. Entanglement is related to wormholes, or ER equal to EPR, that's the slogan. And teleportation is related, quantum teleportation is related to travel through wormholes. Now, there are many challenges to the future. So one is that we don't really know how to derive the space-time corresponding to a given state. So I presented this as we know, but we know what the conjectured relationship is. We don't know how to derive it concretely. And this lack of, and there are many proposals, but they all have some shortcomings. And these shortcomings are related to the fact that we cannot answer this question, which is a very important question, which is what happens at the black hole singularity or the Big Bang singularity? What is the correct description of these singularities? And hopefully, once we understand how to derive the space-time, we'll understand these questions more precisely. Thank you.